Can you still hear me? Yeah.
Awesome.
All right. Okay. So, can you hear me in the back? Great. Okay, so to introduce ourselves. So you have the luxury of being taught by two Serbian professors. How often does that happen? So, my name is Krste, but people call me Krista. So you can call me Krista. It's much easier to say.
My name is Vladimir. Vladimir, Vlad, however you want to do it for short. It's not Vlad Dracula, so don't worry.
Yeah, so we're actually known each other quite a while and actually worked together at MIT on a joint project and still work with that project. And actually, it's in this area of computer architecture, so maybe let Vladimir go tell you about it.
Yep, so as you see up there, there's a little chip. I have also a little board here to show you kind of real scale so you can pass it along. So what you see over there is just a tiny 3x6 millimeter chip and 45 nanometer SOI technology. If you have PlayStation 3 at home, this like older version, there's basically chips like that in there. This one's unique. Besides that it has 75 mil transistors, it also has unique Berkeley RISC-V core, actually two of them. So Krista's group has been developing that. And some of the stuff you'll learn in this course, like instruction set architecture definitions and what's happening underneath, are actually on these chips. But in addition to that and kind of the memory we have on the side, we also adding some novel devices like silicon photonics, enabling these chips to talk much faster to memory, get your gaming going, steamier, and a lot of other applications. So I guess a lot of the course will be kind of driven from these hardware experiences, but also kind of from the software side as well. So let Krste hit it off with big ideas.
So actually, by the end of this course, you should understand things like, what is RISC-V? What does that mean? What's a vector accelerator? You may not quite get to silicon photonics yet, but we'll work on that next time around. Okay, so what we're going to do today is we're going to just start off with a course introduction, get you thinking about machine structures. What is hardware? What is hardware? Now, how does it magically make software run? That's really what this class is about. Then the class has been structured around, instead of giving you tedious details, the big ideas, the really great ideas in computer architecture. These are big ideas that, the foundations of all computer architecture work that's done, but also are things you can take and use in other disciplines. So even if you don't end up being a computer architect, I think some of these principles which came about in computer architecture will be useful to you. So the 6 great ideas we're going to be covering. This is the intro class. So around this point, I'll switch back, let Vladimir take over, and we'll tell you about the class info. I know there's a few questions on the mailing list. We'll go through the course organization, and then we'll start down into how machines represent things. Basically, in computers, everything, there's a number. Okay, so let's get going. Thinking about machine structures. So CS61C, some of you may say, I've done Java, or I've done Python, I just need another programming language, fill out my resume. Well, 61C is not really about C programming. We're going to cover C programming in the class, but only as a way to let you see how to get down to the lower levels of the machine, how to get down to the actual hardware where the work actually happens, right? How do we turn these logical abstractions, computer programs, how do we make them actually do things in the real world, right? How do we connect to physics? And that's really the exciting thing about this class. And we use C just to get you down close to the hardware level. It also happens to be a very useful programming language that's used in many, many applications out there. Variants of it are used as the basis of the iPhone programming environment, Objective-C. It's very common in embedded systems. A lot of high-performance applications are still written in C, right? So it's a very useful programming language to know. But in this class, the focus isn't C per se. It's about the machine structures, how you build machines and how you use them. And we use C just to get you down to that low level. Now, the old days, a class like this would generally be pretty old school. You'd look at old machines, things like this, big ship steering wheel, TV display, old teletype printer. So this picture, I think, has been in this slide deck for a few years. It's actually a complete fake. This is not a computer. This was just done as a joke, Photoshop thing, where it's actually a modern-day submarine, and they've actually added the guy over there in the suit, and they've added the TV. It's actually there used to be a modern TV over there. But old computers kind of look like this, hence the joke. They didn't really have the big ship steering wheel. But, the old days, you thought about the computer, the one computer, right? And that's the way things were structured. But these days, computers are everywhere. So when you think about machines now, there's really these two extremes. At the low end, the small size, very powerful handheld phones, right? So I guess this is an iPhone, so it's not that small anymore, but, kind of small phones, very powerful. The processors in there, I remember when people were just wishing they could have supercomputers as fast as the things you can now buy in an iPhone. So this is one end of the computing spectrum, personal mobile devices. These usually are not that useful by themselves. They have to connect to each other and out to the cloud. And what is the cloud? Where does it live? In sky? No. It lives in data centers, right? The cloud is a whole bunch of computers hidden off somewhere. And where they're usually hidden is somewhere near a river, because they need to cool the thing. It needs to be near cheap power, because they use tens of megawatts in these data centers. And it needs to be in a secret place, so bad guys don't break in and steal all your data. But you can always detect when there's a big building that is a warehouse-scale computer, because it has these massive cooling towers on top. Doing all that computing, you have to dissipate all that heat so the computers don't melt. And so what you see are these massive cooling towers on the top of these big warehouses. That's how you know it's not just a distribution warehouse for Best Buy. It's actually doing computing, right? The massive cooling towers on the side. And if you go inside one of these data centers, all you'll see, this is like the Borg, all you'll see is rows and rows and rows and rows of servers like this arrayed into racks, all wired together. Very rarely, they don't let humans in. Humans tend to mess things up. You don't want operators in there. They tend to trip over things. So mostly autonomous racks and racks and racks of machines. Power up a new piece of the machine, leave it for about 3 years, then power it down, replace it with a new one. Don't go in there because you'll mess it up. So this is, these are this is where the cloud lives. So the cloud lives here, right? And these days, most of the computing you actually do is over there in the data center, right? My other computer is this data center. So in the old days, when we're thinking about one computer, we would teach you this stack of abstractions, going from transistors and logic gates all the way up to programming languages. This is still important, but things have become much more interesting because we can afford to build many, many, many more transistors. And so there are many, many more computers all the way out there in the world. And any given computer has many, many processors inside it. It's not just one single processor. So what we'll be looking at is everything from these massive, what we call warehouse-scale computers with hundreds of things in there. And if you look inside, what's going on? Well, peek inside, and if you look at one individual chip in there, even I need bigger ears. Even a single chip is not just one processor. On a single chip, you have multiple processors. In a server, it's common to have maybe 12 or 16 individual processors on a single chip. And the reason for that is that way they can run in parallel, do more things at once. And that's one of the great ideas in computer architecture, doing things in parallel, doing more than one thing at a time. But even inside one core, a single core just doesn't do one little thing at a time. Even a single core does many things at once. It may do multiple, what we'll call instructions at once. We'll learn about those at the same time. Across, it may do, for example, a multiply while it's doing an add, while it's doing a load from memory, while it's making a decision. All those things at the same time inside a single core, which is just one of many cores on a single chip, inside a node in a warehouse, which may have tens of thousands of servers. So this massive amount of parallelism. And it doesn't stop there. It goes even lower down. If you look inside one of those functional units, they're made of logic gates. So an adder doesn't do like a one little bit carry this. It actually adds in parallel using a bunch of logic gates. So all the way down, you have billions and billions and billions of logic gates working in parallel. And that's the way we get this incredible high performance and why everybody can shift their computing to the cloud, because there's just this immense amount of parallelism there. So it's no good building the hardware, though, if you can't drive it with software, right? The hardware, the only purpose of the hardware is to run software. So, and in running that software, we have to figure out, well, it's great you have all this parallelism. It's great you can do all these things at once, but where do I find that parallelism in the real life, in actual applications? So there's multiple levels of this. At one level is what we call request parallelism. So I do a Google search, you do a Google search, they do a Google search, everybody does a Google search, and you have millions and millions of these searches happening at the same time, and they're basically independent. We may be looking for the same thing, when is next 61C lecture, but everybody's doing it at a different time, different place. They're mostly independent, so that's kind of an easy form of parallelism to find, right? There's lots of people in the world doing independent things, doing independent tasks. So we call that request parallelism. But when you service a single request, when you send to Google a search term, it doesn't just have a single processor handling your search term. No, when you go to Google, you get a whole massive supercomputer doing your incremental search for the next Justin Bieber single, right? There is a huge supercomputer out there dedicated to that. What's happening is your request comes in, it farms out the request to individual sub-pieces of the data set. Is it there? Is it there? Is it there? They may in turn go further on into different subsets of the data set. And so your single request may generate thousands of independent threads worth of work, all just for your single request, right? Your one request may turn into thousands of threads of activity inside that data center, okay? Now, each one of those threads, was Justin Bieber in Mali, or something. There'll be some data set that knows all about Justin Bieber's adventures in Mali. Even the one thread that's doing that piece of the search, that one processor that's handling that one thread, it may be doing multiple instructions at a time to make that one thread go faster. So again, there's another level of parallelism all the way down there. And it doesn't stop there. It goes all the way down to, first of all, once you go down there, you may find I need to look at multiple bits of data at the same time. Is it Mali? Is it Malawi? And in parallel, you can do the comparison. Was he here? Was he there? And so on multiple bits of data at the same time, you can make the same comparison. Okay, so you get this parallelism across a vector of data. We'll talk about that. Then finally, right down at the bottom, you have, like I said, all these logic gates, for example, working together to figure out, does this thing equal that thing? And so you have parallelism all the way down. So in real-life applications, there is an enormous amount of parallelism. If there wasn't, there'd be no point building these massive data centers out of these huge numbers of chips, where each chip has a bunch of cores, where each core has a bunch of functional units, where each functional unit is built from many logic gates. There'd be no reason to do that. Luckily, we found in real-life applications you can harness that parallelism, and that's where we are now. Okay, so we're going to take you through this, and you're going to learn about this through your projects. So just to give you a look ahead to the projects, your first project is really teaching you a bit about this low level of the machine, about C programming, how that kind of program actually runs on the hardware by being turned into instructions that run on the machine. And we'll talk about the machine code. That'll be your first project, just focusing on a single core and how it runs code. The second project will be looking inside and building your own processor, right? So you'll get to build your own processor. This year, you actually get to build a RISC-V processor, which is this new instruction set we came up with at Berkeley. And our idea is to make this take over the world. So you'll be one of the first people building one of this new RISC-V processors, which are going to take over the world. You heard it here first. I'll check back in 5 years' time, and you'll see. You say, I'm so glad I was one of the first to build a RISC-V processor. But you build this up from logic gates. You'll actually see how you can take very, very simple logic gates, connect them together, and make something that can run any program anybody could write. Right, amazingly powerful. It just blows you away every time you think about it. Just very, very basic logic gates hooked together in a certain way can run any possible program, right? Compute anything that's computable. So project 3, you're going to start looking at how do I actually use this parallelism. Now you've sort of figured out how to write a single thread of code in the first project. You've seen the sides of a single processor. In project 3, what you're going to do is on real machines, you're going to try and extract the most performance possible from your own code. So we're going to give you a challenge to, here's this application, we need to calculate something. Go ahead and write the fastest possible code using multiple processors, using all the parallel functional units inside that processor, using the memory hierarchy, which is something we'll talk about, and how do you get the fastest possible code for this particular computation. So finally, we've saved the biggest for last. Oops. The last project, you'll actually get to run your own computations in a warehouse. So we're going to give you accounts in Amazon, and you're going to be running an EC2, and you're going to be doing big jobs, big compute jobs, big data compute, just like the big data guys do in a warehouse, right? So you're going to start an application that's going to trigger off this remote cloud, a whole bunch of servers, somewhere going to run your code to compute something. So that's the final project, sort of tying it all together with the most massive scale computation. Okay, so I told you That's what we're doing in this class. How do you build machines? How is hardware built? You need to understand how software maps to that hardware. But the main part of the course is how do these things actually work? So to get going and to help you understand it, instead of just being a detailed guide through, put this logic gate here, the hip bone's connected to the... Okay, so one of the great ideas is redundancy. In England, you don't get laid off from work, you get made redundant. So I always thought that was funny, because over here that would mean that they would make multiple copies of you. But no, over there it means you're no longer needed. Anyway, great ideas. So these are the 6 great ideas. One is abstraction. So hiding unnecessary details from the upper level, right? So figure out what's actually important to expose at the upper level, and let's hide all the other details so you can focus and get your job done at the next level up in a clean way. The next one is Moore's Law, which is really about designing through trends. This is an incredibly fast-moving industry. It's just amazing how fast things have moved, even in my not so long career. Just amazing how things move, and they're continuing to move. And as a designer, if you actually become a computer architect, you have to understand that it's no good designing for today's competitors. You have to, look ahead a few years where you're going to be. Another big idea is the principle of locality. This is really important. It's part of a bigger principle that programs are actually predictable, which is surprising. Programs don't just go off and do random things. When people write real programs to do real problems, they have properties that you can uncover. And that predictability is something we take we leverage a lot in designing effective computers. And you'll see that predominantly in this class in the area of memory hierarchy. Parallelism, already talked a lot about that. Another big theme is performance measurement and improvement. So, this is an engineering discipline, computer architecture. You're building machines, people have to pay for the components, and people want things to go fast. And we have this continual process of measuring how well you're doing and improving it. So that's an important aspect of computer architecture. And finally, dependability via redundancy. Keeping things running even when pieces are broken. You imagine that massive data center, they're not all going to be working all the time, those computers. In fact, most of the time, some percentage is just going to be off. And actually, quite often, they'll just leave them in the rack if they're broken. They won't even bother replacing them, because replacing them probably means you break something else nearby. So just leave it alone until sometime later it will come up and sweep them away. Okay, so let's get going through this. So the great idea number 1, abstraction. So we're going to go through these levels with you. So right down at the bottom, you can build a computer out of logic gates. Now, those logic gates are themselves an abstraction. They're built with transistors. And if you go down to the details, transistors do lots of weird and wonderful things. But as a logic designer, you don't really care. You just want an AND gate or an OR gate. And so we have these symbols that represent a function, and those are abstracting away all those details about the circuit level issues down below. And come up, you put those things together to make, say, an adder. So you can have a little box that says add. It takes 2 sets of signals in, understands that they represent numbers, does a computation that produces their output as a sum of those 2 numbers, and instead of worrying about the collection of logic gates that does the add, you just put a box and put plus on it. You've hidden the details about how I actually do the add, right? Now, moving up as you cross from hardware into software, we just start thinking about for example, you write a program, it's just going to be a set of bits in memory, just some numbers in memory, right? And it's really hard for humans to just look at long bit strings all day and figure out what's going on, right? And so what we do is we say, well, we're going to put a textual representation of those binary operations, and we call these instructions or assembly level instructions. They're just human readable mnemonics for what those machine code, those binary 1s and 0s mean. And ultimately, these will cause the computer to do something. And finally, even writing an assembly code is incredibly tedious, as you'll learn. And so what we do is we write in higher level languages. For example, C is a much higher level language than assembly code, even though it's a much lower level language than, say, Python. But in C, you can write a few lines that turn into many, many assembly code lines automatically. And that's the standard way people use machines these days. It's very rare that you actually hand code an assembly, except for some very special cases. So you have these ideas of levels of representation, abstraction. Try and hide the details away so you can focus on getting your job done. And so far, if you've taken 61A and B, we've hidden a lot of the details away for how the computer actually works. We're going to sort of peel away the curtain and get you down to how you actually build computers that do things. But ultimately, you may go off and never work at this level again through the magic of abstraction, right? You don't have to worry about this necessarily, depending on what your future needs are. Okay, so this is a diagram, so it's not really turtles all the way down. At the bottom, we hit physics, and that's kind of where the rubber hits the road and machines actually do things. So the second great idea is the notion of Moore's law. So Gordon Moore was one of the co-founders of Intel, who are the number one semiconductor company on the planet. They were actually started to build memory chips, and they did processors as a sideline, as a way of selling more memory chips. So we're making memory chips. What are you going to attach them to? Well, I don't know. Maybe we should build a microprocessor. Okay. Now we can sell you memory chips to go along with the microprocessor. It turned out that memories, a lot of people can build memories. And so that wasn't a very profitable market after a while. So they moved to making very expensive processors. He's actually an alumnus of Cal. So Gordon Moore went to Cal. But at Intel, he got fascinated in the cost of making chips. And back then, your memory was one of the main things they were making. And he was trying to figure out the economics of what is the most cost-effective point to build these transistors. As technology was improving, as people started scaling things down, making them smaller and smaller, he was interested in what's the best cost per transistor at each of these technology points. And at that lowest cost per transistor, because everybody cared about the cost, how many do I get on a die? So he's figuring out the sweet spot of manufacturing, all this stuff. And what he figured out was, with the scaling the way it was happening, every 18 months or so, you could double the most cost-effective number of components on a chip through scaling. So that's quite exciting. That's an exponential, right? So doubling every 18 months to 2 years. And he did this in 1965, looking back a few years. And what's surprising is this has just kept true all the way through until recently, right? And that's really what's driven this whole industry, the fact that the guys building these transistors have figured out how to shrink them and shrink them and shrink them and shrink them, lowering the cost so we could afford to put them everywhere. You all have billions and billions of transistors now, billions of them, every one of you, right? And you probably have dozens and dozens and dozens of microprocessors. And that's only possible because it's so cheap to build those transistors. So that's great. So if you're a computer designer, back in 20 years ago, there was this really hot time in computer architecture where people were focusing on single processor workstations. And they were improving by about 50 or 60% per year in performance. That's a factor of 1,000 in 10 years. So 1,000 times faster in 10 years. That's how fast things used to be. And as a designer, if you proposed a change, it better take, for every week it took to implement that change, it better cause at least a 1% improvement in performance. Because if you delayed a project by a week, everybody else got 1% faster because they're on this curve. Incredible times. But things are changing. There's those proverbial Chinese curse about, may you live in interesting times. As architects, we're living in very interesting times. So remember, Moore's law was about, at the sweet spot of manufacturing of, what's the cheapest cost per transistor, how does the number of components change? Well, as they've been shrinking and shrinking, those guys in the process technology world are just magicians, keep pulling new tricks out of the hat, but they're kind of running out of things they can do to make the transistor smaller, because ultimately they have to make them out of atoms, right? If they're going to live in this universe, they have to obey physics. And there's fewer and fewer atoms left to scale. And it's incredibly difficult to pattern these transistors, to actually draw them or image them onto the wafers when they're fabricating them. And it's turning out that now that they can make them smaller, but it takes longer to make them. And this fabrication plant is really expensive. They cost, $5 or $10 billion each. And every part that goes through there has to pay some of the cost of that big plant. So what's happening is they've shrunk them down, but it takes longer to make them, so each one starts to cost more than the bigger one from before. And so this completely flips over Moore's law. So instead of the new, smaller transistor being cheaper, it might actually be more expensive. And this is, the end of, basically the end of Moore's law. And so you will see this. It's basically already kind of happening. There are a few naysayers, a few end of Moore's law deniers, but it's kind of happening. And next few years, you'll see it's just slowing and slowing down. And there's really nothing, because the industry doesn't want smaller transistors really unless they're cheaper. It's all about cost. Very interesting times. So this is a different kind of trend you have to live with. Okay. One great thing about computers is they can access lots of memory, lots of storage. That's most of what they do is touch data, do interesting things with it. And in computer systems, you find there's many, many, many different kinds of memory. It's so important. That's what most of the computer is memory. And one thing you realize, basic physics says it takes, the speed of light. I can only go so far in a certain amount of time to access something. And so intrinsically, as you make memories bigger, it's going to take longer to get to some piece of it, right? You just can't, pack it in. So it's good that you can make bits smaller and they get closer, but as we saw, there's a limit to how small you can make things. So fundamentally, the bigger things are, the slower they are in terms of memory. And in computer systems, what's amazing is architects have figured out how to deal with very vast differences in the access times of different components. I'll just quickly do this. We'll do this more thoroughly later in lectures. But the very fastest pieces of memory on a computer, right in the middle of the processor core, right next to the functional units, those are called registers. And they may be accessed multiple times in a single clock cycle. So say like a nanosecond. There may be a bit bigger lump of memory that's called the on-chip cache. And this may be, tens or hundreds of kilobytes, maybe a megabyte. And this you can access in a few nanoseconds, so just a little bit further away. Now, once you go off the chip, there's suddenly a big cliff. It's like, it takes a long time to get off chip because I have to take my little signal, get to the edge of the chip, and then have to buffer it up so it's ready for the great outdoors, getting off the chip and out into the real world, hitting big signals. And then I hit some large memory chip like a DRAM chip or a DIMM that you plug into your laptop. Now, those may take 100 clock cycles to access. So 100 cycles. If I'm working on chip, 1 cycle. Off chip, 100 cycles. And most of your memory is off chip, right? 100 cycles away. That's really slow. It gets worse if you actually touch a rotating disk. How many of you have a rotating disk in your laptop? Okay, very few. Oh, CD-ROM or a magnetic disk, rotating magnetic disk. Just a few, okay. Well, they're really slow. It's a good job most of you got rid of them. They're like a million times, millions of cycles to get to those. And what people use for storage, archival storage in data centers is tape, and that's really, really slow. Like, forget about it. You sort of put it in order, and a few days later you get your data back. Give you some idea of the sense of scale. If you think about registers are kind of like things in your head, and a cache is like things in this room. A cache near the processor might be like somewhere on campus. But off-chip memory, DRAM, that's like going to Sacramento and back, to get something. It takes a long time to get there. And going to disk is like going to Pluto. Like it's just so far away. And forget about tape. That's some future, further galaxy away. And these scales, you often, it's very difficult to comprehend how people actually manage to get anything running at any speed at all with this. Because most of your memory is the slow stuff, because that's the cheap stuff. The big slow memories are where most of your data lives. The thing that saves us, that actually makes computers work at all, is one of these big ideas, the principle of locality, and this idea of a memory hierarchy. It turns out that people don't write programs usually that randomly touch any piece of data in the whole space of all the data you have in your machine. You just don't do that. When you write programs, pretty much every single program people write has a lot of what we call locality. What that means is, if you touch a piece of data once, it's pretty likely you're going to touch it again sooner, or much sooner than you're going to touch any other bit of data. And what that lets us do is cache that bit of data you just touched and use that piece repeatedly without having to go all the way out to the big memory. And in modern machines, the memory hierarchy is very deep. We'll go through all these levels later. So that's one of the big ideas. Principle of locality. If the programs didn't have locality, our computers would run as slow as the largest big memory that we had on there. So, rotating disk, if you still had that in your laptop, that's how fast your computer would be if we didn't have locality. Fourth great idea is parallelism, doing multiple things at once. Right down in the machine at the low level, we have multiple instructions and execution at the same time. When we're working on some single application, we may break it up and assign different bits of data to different units to do that in parallel. And the big scale, if different people are coming in making requests, say the Google warehouse, we do those in parallel. So parallelism is one of the key things. You'll see that at many, many scales in this class. The one thing to remember about parallelism is that has a limit. It's great that you have 100,000 processors ready to do your beckoning, but if you cannot write a program that is almost entirely parallel, you won't get much performance gain. So Andal's law says, well, if 10% of my program I have to do sequentially, it doesn't matter how many processors I have, I can only get a speed up of 10. I can take the other 90% and speed it up infinitely fast, but I still have to do the sequential piece, right? So we'll get to Andal's law later, but there's a limit on how far you can go with parallelism, depending on how much you can parallelize your code. So another great idea is just actually measuring your code, figuring out how fast it is and tuning it to match the hardware to get good performance. You'll be doing this in Project 3. You'll be doing a lot of work on actually tuning your code and making it go really fast. And you'll see that from your initial naive code to the final code, you'll see integer factors, big integer factors improvement in performance. And if you're good at this stuff, you'll easily get a nice job at one of these big companies because they really care about efficiency from these machines. They wouldn't buy 100,000 servers if 10 would do, right? They really want to make good use of all that hardware they have there. Now, so this last one is really about coping with failures. So if you think about these data centers, let's just do a little example. Say each server had 4 disks on it, rotating disks, big high capacity rotating disks. And the failure rate of those is something like, on average, about 4% a year are going to fail. So what does that mean across this whole data center? How often does a disk fail inside a data center? It's every month, every week, every day, every hour. Well, if you work through the numbers, that's 200,000 disks total. If on average 4% of them fail in a year, that's 8,000 disks failing in a year. There's about 8,700 hours in a year. So that means, about 1 an hour is failing in a data center. So all those massive cloud databases are highly, highly replicated and backed up because the disks underneath there are failing constantly. They're just, going out all the time, right? So they have to design all the file systems to make sure they keep running even though this is happening under the hood. So the fun one, this is from the news. Just been reading about NASA has a similar problem out in Mars, right? So out on Mars, they launched the rovers Spirit and Opportunity a long time ago. I think it's 11 years ago now. And they're still running. Right? It was amazing. They're supposed to last for 3 months, and they're out there for 11 years still capturing data. But recently, Opportunity, one of them, its memory started to break, the flash memory, like in your SSD drives, right, or in USB keys. And basically, it's worn out. So solid-state memory like flash actually wears out. What's happening is you're moving electrons around to store state, and it's sort of disturbing the atomic lattice in there. Every time you do that, there's high voltages being used, and eventually it just wears out. And so that's happened on Mars, which is a bit of a problem. It's kind of hard to go up and repair that. So what they've actually done is that they're sending a new software update that tries to avoid using the pieces of the memory that have worn out so they can keep going, right? So there you go, reliability in action. So this great idea, the last great idea is really dependability via redundancy. Because real hardware fails, you want to add redundancy so that if one of the things fails, the other pieces can continue. So this little example is I'll build 3 adders. So if I find out that one of them is giving me the wrong answer, I'll just use if 2 out of 3 agree, I'll use the majority as the right result. And then things keep going. And this we use all the way from data centers to storage to memory to instructors, right? So instructors, yeah. Redundant data centers. So actually what's interesting, places like Google, whatever, they make sure that if one whole data center goes down, like, Atlanta gets wiped out for some reason, they still keep going. Usually it'd be something not so exciting as, somebody switched off the power accidentally but they make sure that things keep going across the whole, at the metropolitan scale. Within disks, you've heard about RAID, maybe. You've used RAID, redundant disks. So one disk fails, the other ones can recreate the data, and you can pull out the failing disk, plug in a new one, and rebuild the replica. The memory DIMMs in high-end machines all have extra bits, so they can tell when something's gone wrong, the extra redundancy. And we have 2 microphones, luckily. Okay, well, so that was a whirlwind tour of the class. I can now hand over to Vladimir to tell you about the actual course details.
We're now down to one microphone, so hopefully things work out. So, yeah, this is a little bit about the class mechanics. And, as great master says, always in motion the future is, which means with such a big class and a lot of things going on, there will be constantly some things fluid and changing. So make sure to be well plugged into the announcements and what's happening on the website. We're going to use Piazza, as I'll mention, kind of for all the notifications and more. So make sure that you are tuned in. And we're going to be announcing that in class as well. I'll show kind of what the class dynamics is going to look like and where you can expect to get plugged into that. Here is roughly how the weekly schedule will look like. And this kind of a red line kind of shows you kind of where the break in the week is. So things will always start on Tuesday in terms of new topics and kind of new things going on that will cover the homework assignments that follow and the lab. Again, sort of lecture followed by discussion sessions, and then we're going to hit it off with labs that kind of address these issues. Again, project will be kind of then moved to, once you've absorbed all that stuff and done it in the lab, you're going to start try to hit it on in the project as well. The main source for the information for the course will be sort of the 61C website. It's not B courses. It's publicly accessible, so all the material is going to be there. There's actually a web page with pictures of all the GSIs. I'd like to ask the ones that are here to stand up. They're really the strength of this class, okay? So we have 3. Sagar is the head TA, so he's running the ship pretty much. Kirsten are just tagging along. And you'll find the GSIs to be extreme source of support. And I would say, so let's give them a hand in advance, because you're going to want it. Yeah, thanks, guys. We have some superstars in the crew and are also constantly looking at great people who do well in the labs and stuff. And I'll talk about the kind of the altruism a little bit to essentially give back. And once you're going through the class, kind of turn back and help with other classes A and B, but also like once you've gone through, come back and try to help us out with future generations in 61C. We're going to have about, on average, 15 pages of reading per week. It's the 5th edition of Patterson-Hennessy book. We're going to try to help you out with the 4th edition if you have it, so it's okay maybe to stick with it. Most of the content will be really given through the lectures in class. Another classic book it's a very good reference for you to kind of use is Ritchie, C programming. And the Data Center as a Computer book is actually on the website, so you can download the electronic version and just go through it. It's actually a very fun read. As I mentioned, Piazza is really going to be heavily used, and not only for us communicating to you, but really as a means for people helping each other. And you'll see that in a class this big, it really does make a lot of difference. So another request we have is, since there's going to be lots of posts and actually lots of good Samaritans helping out, kind of answering these clarifications, please read kind of the thread, right? What's been said before just shooting in a question. Piazza is very searchable, so you can kind of search for things before you kind of go in and do a millionth post on the same topic, right? In terms of the course grading, I'd like to first single out this EPA concept. It's effort, participation, and altruism. It's sort of a soft 5% of the grade that we're going to kind of go in detail through what these concepts mean, but it's essentially a way for you to give back to the class and actually get something back in return. It's usually almost kind of grade that can make a difference in the end. Homework is about 10%, labs 5, projects about 20, and as Kirsty already mentioned, there will be 4 projects that sort of build up on different parts of the course, so very useful to cover. This time around, we're going to have 2 in-class midterms, and then a final. So midterms will be here in class in, I guess, week 6th and 12th. The good thing about these midterms, or how we're doing it, is midterms can be clobbered. It means if you mess up some concept on a midterm, and there's a same concept on the final that you ace, well, you're done. You don't have to worry about the midterm, right? So all that matters is that you exit the course knowing the material, right? So that's all we care about. So we're going to apply this policy. It used to be it was done in previous terms, worked well. So we're all for you guys learning this stuff kind of as you exit, and don't stress about kind of, little issues along the way. But make sure that you've done the midterm, because if you screw up on the final, then kind of, that midterm grade will help you, right? So it goes the other way around too. We will have kind of, as Krista said, like code tuning project where there will be kind of performance competition for that kind of the highest performance thing. And so, with some certificates, I guess, issued and, claps and stuff. So stay tuned. And then also for the EPA, in terms of who gives most of the class. We're going to also, this time around, use the sort of peer instruction, in a sense that lectures will be broken kind of in several pieces, and we're usually going to have a little question up there to kind of break the flow and get you spinning wheels a little bit. And usually what we're going to do is let you first answer, and then we're going to let you kind of talk to, get introduced to a person next to you, and then discuss it a little bit, and then try again. So we're going to see how well that peer instruction works in real setting. And we're going to use clickers for this. So the change this term, simply because it didn't actually end up working that well for a lot of people last term, we're not going to use web clickers. It's only going to be the hardware ones. There's a lot of issues with authentication, things like that. But, you can kind of resell these, and so it's not going to hopefully be a big hit on the budget. The clickers and your answers are not going to be kind of as a correct answer or false answer. They're not going to be part of the grade in that way, but it's really just part of the participation, and I'll talk a little bit about that in the EPA. Really, it matters to us that you give us instant feedback on what you're understanding, and we want to basically be able to tailor the lectures and our explanations that way. So clickers are really more for that than really grading you on every single A, B, or C that you click there. If you go on the website, you can kind of see the ECS grading policy for courses, lower division, upper division, stuff like that. This is just sort of to give you an idea of the expected average GPAs. From what I heard from instructors in previous terms, usually this course is not graded really on a curve. Okay, so there's some kind of absolute settings, but it sort of ends up being this kind of distribution, right? So again, what matters to us is that you learn the material, not really how many A's or B's we have. Even though there's kind of generally in the nation sort of the A's inflation kind of thing, really, if you've done your stuff, don't worry about being graded on a curve and pulled down. Our goal as instructors, of course, to make this course really fun. I hope you got excited by some of the big things that Kirsta was talking about and the project. I'm really excited to kind of go back and kind of hack that stuff as well. And so I think you're going to learn a lot. We really are all pro students, so through some of these things like really interaction in class with clickers and also the exam clobbering, we're trying to figure out the best way to help you out get through this material. This is not an easy material. You're going to learn a lot and work hard, but that's what matters. And the exams, projects are all going to be pretty rigorous, but after you go through all that, you'll be able to kind of show some ECS muscle. Our goal is to really score 7.0 on HKN, not really because we just need that grade. It's actually because we want to have you guys understand this stuff and have you have a fun experience in that. So we're listening every lecture, post-lecture on Piazza, any feedback you have to get us going in a direction where you get it better. That's what we were looking for. Okay. There's some, I mentioned this EPA kind of concept about 5%. So it's effort, participation, and altruism. Effort is really attendance. So come to lecture, come to the office hours. I think we have about like 90 hours of office hours, right? What's 14?
90 hours of
lab. 90 hours of lab and 14 hours of office hours per week. Okay. I think that actually doesn't include Krista's and mine. So there's plenty of opportunity to interact with people, and please take advantage of that. We're here for you. Participation by attending lectures and just clicking, doesn't matter if you click right or wrong. We will register that, and that will be part of this 5% of the grade. Basically, are you interacting in the class? Altruism, I would actually say, is probably the biggest of all these in my book, and this is really helping others, like helping get the class go. So if there's a post on Piazza, you know the answer. Please jump in. We have a lot of GSIs, but still the ratio of GSI to student ratio is pretty big. So please help. If you know the answer, if you're done with the lab, and there's been great examples in past terms, people early done with the lab, they know that stuff. They don't just stand up and go home. They stand up, come to the GSI, ask, hey, can I stay and like help other people? And we really appreciate that, and that's the path to being, the LA and reader later and helping out with the course. And so we really, really appreciate that. I think that's kind of the biggest one in my book. There's some unpleasant stuff we have to deal with. Everyone has a problem once in a while. They can't turn the homework in. They can't turn the project on time. We don't want to know what the problems are. It doesn't really matter. We just want to relax you and tell you, look, you have 3 slips. So you'll get 3 tokens. And if you're a minute late beyond like 11:59 p.m., go home, sleep. Okay? Use that token, spend a few more hours next day working it out, finishing, and turn in. Every time you use up a token, so if you use up all 3 tokens, every day you turn the thing late is 33% hit on the number of points. Okay, so since the project is worth kind of much more than the homeworks, usually people save up the tokens for turning in projects a little bit later. There is some kind of dance there if the 2 project partners have been using the slip tokens at a different pace. So I think we do the minimum, right? So be careful there. Talk to your project partner. Make sure they haven't used up all the slip tokens very early on. So coordinate. Even more unpleasant stuff, but we sort of have to put this one slide. It's a really big class, not as big as the one in the fall, but still very big class. Lots of hard problems. But one thing we're going to do is make sure that all projects are done with a partner. So you have a shoulder to cry. But only one shoulder, okay? So that's your soulmate. That's your, person for, this semester. Person who you will bounce ideas off of and really get the projects done. No one else should know what you guys are discussing, how the algorithm works, how you're implementing it. Sometimes the trick is just in the algorithm, or not really the C or any sort of code implementation is rather trivial. But those few lines, how you do it, the concept is really all that matters. So please, we're going to be looking at these things. And even if you just discuss the algorithm, the code may end up being identical, and we have means to check all that stuff. And then unnecessarily, you're going to create problems for yourself. The point here is for people to learn. We give you that one peer with whom you can really go through this and learn. but everything else you need to hand in yourself. Don't be messy leaving your code, leaving your workstation open, things like that. There are people who will come in and maybe take your code, and then both the giver and the receiver really get into problems. Okay. You can read this at your leisure. I don't want to kind of be the bearer of unpleasant kind of bullet items, but please make sure to read this. You'll be reminded in the labs and about this stuff. Just in terms of the architecture of the typical lecture, as you all know, the attention span at the beginning is great. People are really gang-ho and going, and right about, I think, when we handed it off, there was a little bit of, okay, we've mastered the 6 great ideas, so we got it, right? And really, that's where we start doing this. We're going to be doing at least the clicker check and the administrativia for the class regularly. Then I get my round, and you're up again. And then, again, kind of dozing off. And then that's where we're going to hit you with some news and fun stuff. And then again, kind of toward the end, another segment, right? That will be kind of the conclusion, and then hitting it off to another class where, again, you have kind of peak attention. So another thing I didn't mention, which is kind of the way we would like this auditorium organized and kind of the lectures to go, is that we would want to be able to allow people who use electronic devices for note-taking, because we're not doing handouts, but we're posting the PDFs before the lecture. So people who want to use laptops and tablets for note-taking, we would like them to be kind of in the top rows and kind of here at the bottom. And then everyone else who's just like old-fashioned to be somewhere in the middle. And the main reason for that is we want people to be able to focus on what's up here and us, and really try to get the material. If you have a laptop and you're watching a very fun game or playing Halo or something like that, you kind of distract people around you. You can do that at the top or somewhere here. That's okay with us. It's your call. But try not to distract other people. I think that's kind of the main thing here. Okay, so any questions about the class? Anything that I've covered so far, or maybe pieces that Kirsta covered? If not, we're going to just jump into some of the class. Yeah?
So for the non-cheating policy, how much are you allowed to talk to people that aren't your partner about projects?
For the non-cheating policy, how much are you're allowed to talk to? Any experience from past terms? Don't talk at all.
Anything less than pseudocode is okay.
Okay, so anything less than pseudocode. So pseudocode is not okay. Not even, and that reminds me, if you go to a tutoring session, pseudocode is not allowed, right? Because you may get tutored, one type of pseudocode, another person, same thing. You end up with same solutions. Bad, right? There's lots of help, GSIs, LAs. Please use it. It's really, and your partner. I think it should be enough of a support structure. And really the key is that you'll learn. If we teach you to catch a fish, that's good. Or if you try to teach other people, just have that in mind, that explain to them how they should think about coming to a solution rather than giving them the solution, right? At any piece of kind of any step of the way, right? Even if you volunteer to help around in the lab or stuff, and people ask you accidentally about the homework or the project, that should be there. Any other? Yeah?
Regarding the slip days, if you use 1 minute, do you have like 71 hours and 59 seconds left? Or during this left? Or is it like...
Great question. It's about slip. 1 minute equals 1 day. So just sleep it over and do it at your pace. Yep.
Do we have to attend the lab and discussion that we have enrolled in, or can we attend any one which we want?
It's a question about lab and discussions. I'll leave it for Piazza clarification, so we can maybe... It's already on Piazza. Yeah. Yep. Is the exam open book? I would say we haven't decided yet. My inclination would be no, and two pages likely cheat sheet allowed. Not because we don't like, we're really rigid, but because actually, if you bring like a ton of books, you'll waste more time digging through them than actually doing the exam, right? And so, yes, and then paper rustling and stuff like that, like people get annoyed. Yes.
So is the deduction of slip days automatic?
Deduction of slip days automatic, yes. Okay. For all the other logistics, I can either answer after class or just post on Piazza, and we'll go through that. Okay, so we're going to hit it off with some of the class material. At least, I don't know how many of you kind of know the story about the number land and a word land, right? Where some people believe words are everything and some that numbers are everything. Here, because we're kind of on ECS, we'll say that everything is a number, right? At least everything we can try to represent as a number, or at least everything that a computer knows how to interpret can be represented as a number, which means mostly information, right? Information I can encode as a number, and that's exactly what computer does. It encodes information, whether it's instruction on what to do, whether it's data. It will represent it as a number and then go execute on that. And usually, there are some computers, some early attempts that don't really use binary. That's kind of fuzzy logic and stuff like that, probabilistic computers people are trying to build. But by and large, today's machines are really using binary arithmetic. So it means represent a state as light or no light, 0 or a 1, and then try out of this to build out information. Right? So the way you would group them is as kind of 8-bit bytes, 16-bit half words, 32 bits we call a word. A bit is like a 0 or a 1. 64-bit would be double words. These kind of correspond to kind of C types as well, so you'll get familiar with that too. And then if you start doing integer arithmetic or floating point arithmetic operations, because of this limitation in how many bits we use to represent a number, you may end up with some weird cases or corner cases that are called overflow or underflow, where your arithmetic is just going, your number that you get is not really going to be the right calculation, right? And we have ways of actually, as you'll learn today, to recognize these kind of cases and then correct them, right? But this will make us actually be able to use this fixed size number representation to do lots of different things. So here is an example of the number representation. You're all familiar with the decimal system, right? And so that will be something of the sort of d times base to the I, where d is a digit, and base is, let's say it will be a decimal or base of 10 in our decimal system. I would be the place of the digit in the number, right? So if we do 123 or 123 in a decimal system, that would be 1 in the place of hundreds, 2 will be in the space of tens, and 3 will be in the space of ones, right? And then we're going to write it down like that and be able to sort of add all these things together and indeed get 123, right? So same thing happens if we represent things now with binary numbers. In binary, we would use base 2. So every place will be worth an increasing power of 2. So the rightmost digit would be digit times 2 to the 0. The one next to it would be digit times 2 to the 1, etc. And then we'll be able to, again, create numbers that way. If you move the notation to base 16, we'll call it hexadecimal, base 8 octal, and things like that. Yes?
If you had numbers in different bases?
Can you have numbers in different bases? You can. You would have to convert from one to another. This, in fact, d to the base I is the way to kind of convert between things. machines that kind of operate in multiple bases, the computation is not very efficient, so you tend to stick with one representation. Just in this class, you may not have seen it before, we're going to use this notation at the bottom where we put a little letter, so the letter like 10 or hex or 2 will essentially tell you what the base is, just so you don't confuse it with a digit, right? So the subscript is going to be 2 in words rather than a number, just so you don't get confused. Later on, we'll just drop that. But for now, just so you have it. So let's do some examples. So the hex digits, you start from 0, you do 1, 2, 3, you do up to 9. Normally, then you run out of digits. So then you have to use something else, so people started adding letters. So A is a 10, B is 11, F all the way up to 15, which is F. Okay? And then if you write that number, again, in the hex notation, for example, we'll have F, 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 hex. Again, the first F on the left is 15 in the decimal notation times 16 square, right? Because it's the third position, so 0, 1, 2. So the base 16 gets a power of 2. The next digit, again, 15, but now the weight of that place is only 16 to the power of 1. And then the last one is 15, but the weight of the place of the rightmost place is really just 16 to 0. It's the units place, right? And then you can sum them all up. Now we're summing a hex number. We've transitioned it to the decimal base, and we find an equivalent, which is in this case 4,095. Now, on the next bullet, we can represent that number also in binary. Every hex digit, let's say F, will be 4 binary numbers, or 4 bits, and F will be 4 ones. Right, so if you start counting, 4 zeros will be 0, 4 zeros and a 1 will be 1, 2 zeros, 1 0 will be 2, etc. As you come going up, all ones, 4 ones will be 15. And so you will break it up, and what we do here is we do in groups of 4. So you see that there's 4 bits, then a little space, then 4 bits. You can really just jam that all up together, but we do it like this because it's easier to parse. You sort of look at 4, you say, okay, this is a nibble. Okay, I know it's a hex number. The next one and the next one, right? So it's like commas when you put like 10,000, 10 comma something in decimal system, right? Okay. You can have signed and unsigned numbers as well. And pretty much C, C++, Java, if you use it, you can have a 7 and a minus 255. And really all you would do is type int XYZ. That's it, right? Now, C and C++ have also unsigned integers, which you're not going to use for computation, but really for addressing. You cannot have a negative address. Address space is from 0 to something, right, to your capacity. So you'll be using unsigned ints for computing the address of data, byte or word to access. 32-bit word can represent 2 to the 32 binary numbers. Right? Just think of a 2-bit word, right? We have 0, 0, 0, 1, 1, 0, 1, 1. That's already 4 numbers, right? So 2 to the 32 will be 32-bit word representation. So these will be between 0 and 2 to the 32 minus 1, which we're just going to call this for short 4 gig. Okay, so 4 gig of address space. Whatever the word size is, if the data we're trying to fetch there is a byte, this would be a 4 gigabyte address space, right? If it's a more than 1 byte word, it will be 4 gigawords address space, right? Notice this is not 4 billion. It's 4 billion plus some change because of this power of 2 kind of stuff. Now, the way you would represent binary these integers is just, again, as we did with these like nibbles of 4 for easier parsing. 0 in the tens notation will be In this case, we have 1, 2, 3, 4, 5, 6, 7, 8 times 4 bits, so that's a 32-bit representation, right? And we're going all the way from 0 to 4 billion or 4 giga addresses. Now, that's unsigned. If we wanted to introduce sign, we need to give something up, right? I cannot have a sign and also from 0 to 2 to the 32 minus 1 numbers, positive numbers, right? Because I've introduced this 1 bit for the sign. And there's been many different kind of representations of sign numbers in the history. We're not going to teach you any of that. We're just going to focus on the one that computers use today because it's actually pretty nice and has survived all the kind of variations. So it's a 2's complement representation. So really what we want as programmers, we want to have 1/2 of all the numbers to be positive, all the numbers that we see, right? 1/2 to be positive, 1/2 roughly negative, and then we want only 1 0. Right? So that's how we used to kind of see and learn computation. So that's exactly what 2's complement does. And in order to generate a negative number, it picks a positive number and looks at how far that number is from 2 to the n, if I have n bits. And then represents that number in a binary way. And that will be kind of the mirror image of the number. And I'll show you some easy ways to do it, so don't be like, oh, it's too hard. So in this world, I'm still going to use 32 bits, for example, to represent a number, but it's going to go from -2 to the 31 through 0 to 2 to the 31 minus 1. So I really have one more negative number than I have truly positive numbers, but 0 counts as a positive number. So you have sort of equal number of positives and negatives, right? So that will be kind of the range. In the book, you have some kind of other options, but this is pretty much what we're going to use. The other thing is, good news is computers use this today exclusively. So you're not wasting time learning some other representations. The good thing about 2's complement also, just by looking at the number and seeing the first bit or the leftmost bit, you will know whether the number is positive or negative. It may not be as easy to see immediately what the number is, but you'll know that it's positive or negative. So let's take a look at one representation. So same 32-bit space. We just had to give up now half of the space for the negative numbers. And look at how it goes. So it starts from 0. It goes increasingly all the way to 2 giga, right? So 2,147,483, meaning 0 and all ones. Right? That's the highest positive number I can represent. If I add one more bit to this, I will get to 1 and then all zeros. But that 1 already has a sign bit change. Okay? So it will actually belong to the most negative number. Right? And this is what we're going to later refer to as overflow. If you go during some computation from this most positive number all the way down to the most negative number, it will be an overflow. You're kind of overflow, right? It's a water flowing out of glass. Similarly, if you're now going from 1 and all zeros, and then adding stuff, and you're going inching all the way up to the -1. So we'll see kind of the underflow will be the other way around, where you're going from the most negative number up. Right? So maybe a little bit confusing at this point. Let's see some ways how to easily make these 2's complement numbers. Okay. So the definition is kind of, okay, for an n-bit word, just take a number and look at its distance from 2 to the n. So an example. Take a 4-bit number. Let's say 3 in the base 10. We would write it as 0011. Right? The 2's complement, I know since this is a positive 3, the 2's complement I want to represent is -3 in the decimal. Right? So then I'm looking at the difference from 16 to 3, because 16 is 2 to the 4. So I'm representing this as 4 bits, so 2 to the 4 is 16. 16 minus 3 is 13. 13, I just go and represent binary, and that's actually 1101. So that is actually going to be the code for minus 3. Okay. Now, this is like, oh, this is crazy. Okay, who's going to do this all the time, right? Well, there's an easier way. And this is actually how computers do it. And when you go down to the build an ALU and you want a subtractor instead of an adder, you would do it exactly this way. So it's actually much simpler than this. You will take your original word, you will invert all the bits, and then just add 1. That's so super simple. Inverter, kind of that function not, is sort of the most primitive logic gate. So it's very easy to do. And in fact, an example is here. I take 3, so 0, 0, 1, 1. I'll flip all the bits, so make it 1, 1, 0, 0, and then just add 1. Right? There you go, magic. Boom. Okay? So I like that method rather than doing kind of the subtraction thing. Okay, so let's take a look at some of the examples here. On the left, we have 3 plus 2. So this is, with binary numbers, the way you do summation is just like you learned in elementary school, right? So it's actually even simpler because you only go modulo 2, right? So 1 plus 1 is actually 0, and the carry is a 1, right? So we would go on the leftmost example, 1, we just write it down. 1 and 1 are 0, carry over, right? So that will be 5. And then 3 and a minus 2. If I want to subtract 2 from 3, I would first write that 2 as minus 2, and that will be in 2's complement. So minus 2 would actually be 1, 1, 1, 0. And then I just go and add them. 1 and 0, 1, 1, carry, 1, 1, carry. And what I get is the carry out of this 4-bit word. But because I only represent numbers in 4 bits, I'm just going to ignore that one number, right? So this 1 over here I'm going to ignore. Okay, so I'm only looking at these 4 bits, right? And those 4 bits tell me it's a 1. So it's a 1 decimal. Okay, minus 3 and minus 2, again, I'm going to represent both numbers in 2's complement and then just add them, right? So that will be minus 5. And I, again, ignore this 5th bit that gets produced, right? That's sort of the carry out of the summation. Now, in this case, I get a little bit of a problem, right? So here, look, I just did the addition. I should get an 8, right? But remember, these are 2's complement numbers. The moment it has a 1 at the most significant bit, which is the leftmost bit, most significant bit is the bit with the highest weight, right? So in this case, that bit would weight 2 to the 3, or weight 8. So if it was unsigned, yes, it would be an 8, right? But this is actually 2's complement, so that bit indicates a sign. So this is actually minus 8, right? Which is obviously a wrong answer. So this is this overflow that we talked about. Like you're at 0 and all ones, you just add one more drop, and you overflow the glass, right? So you drop all the way down to kind of the lowest negative value. Now, similarly here, I have minus 8, and I subtract 1, so I'm supposed to get minus 9, right? But I don't have that much space, and I'm circling back to plus 7, right? So that's the underflow. How do we detect these cases? This is very harmful to your bank account if you go and do this type of thing, right? Imagine this, like I'm maxing out and then all of a sudden 0, right? Or I'm actually in debt by that much, right? That's very bad. So the good news is actually that if you analyze how the carries work, right? If you looked at these 2 top cases, the carry into the 4th place was essentially a 1, and the carry out of the 4th place was also a 1. Right? That's this 5th bit we don't care about. these two are equal means computation is okay. So I can safely ignore that one bit. So when we do computation, we check carry into MSB and carry out of the MSB, and we say thumbs up if they're equal. If they're not equal, you are getting an overflow and underflow condition, right? And then you can go throw an exception, do some correction there, and change that. Okay, little quiz. We don't have clickers yet, and this is actually something that reminds me at this point. When you buy the clicker, go through the iClicker website, register your clicker. So next time you bring it in, on Thursday we already have a station, so we're going to try to do some clicking and register then your clickers and then do web sync to actually get the roster. And from that point, we'll be able to count your responses. So if Thursday will be the setup, we're not going to take that into account, but from then on, we're actually going to be taking things into account. So please, if you can bring stuff on Thursday, would be great. Tuesday at the latest to kind of click and synchronize. So the question here is, if I had a 5-bit word, what integers can I represent in 2's complement? And maybe I can get a show of hands for like first answer, second answer, third, okay, fourth. Woohoo! Okay, got it. So the homework will kind of cover these number representations. We're not going to bother you with other types, so just unsigned and signed, and 2's complement signed. So hopefully you get some time to brush up on this. Just in summary, kind of what we covered here is 6 big ideas. Just scratch the surface so you guys will be able to dive in, and everything's a number.